Hi everybody, we're going to finish up our slides on chapter 9. You're going to have to bear with me a little bit. I'm sure my voice does not sound pleasing while you're listening to this video, so I apologize ahead of time. This is the last slide that we left off on impulse and momentum of a system of particles. Now, the last few slides that we looked at had to deal with the velocity in terms of center of mass. We also looked at acceleration for center of mass, and all of those things we've seen before. We know that if we take the derivative of position, we can get our velocity. We know that if we take the derivative of velocity, we could get acceleration. So in terms of center of mass, there's nothing different. We're just taking the derivative for the velocity at the center of mass, and then that's how we're going to get our acceleration for the center of mass. The last thing I think that we saw on the video from today was in terms of Newton's second law and thinking about center of mass. So that would be that the sum of the forces, and specifically let's talk about the net force, would be equal to capital M, which is representing that total mass, and then acceleration, specifically the acceleration at the center of mass. So this is still Newton's second law. We're just saying that the center of mass of a system of particles now combined mass, which would be our representation here of capital M, is going to move like an equivalent particle of mass M that would move under any influence or under an influence of a net external force. So if I apply some force to the center of mass, of course I'm going to get that center of mass to have an acceleration. So we can show this also with Newton's second law. The last thing that we kind of want to talk about in terms of thinking about center of mass and then systems of particles would be impulse and momentum. So in terms of forces, because I think that's the last thing that we really talked about. So the impulse that's, let's say, imparted to a system by some external force. So we know that impulse is just an external force that's being applied, or a net force that's being applied in a time interval, and we can think about that by our impulse formula, which is just the integral of the sum of the forces. Specifically, let's talk about the external forces in a time interval. So I have my integral of the sum of my external forces, and then in that time interval. Well, I know that external force is also just equivalent to mass times the acceleration of the center of mass. So instead of writing the sum of the forces in my integral here, let's substitute in what we also know for that, which would be total mass times that acceleration of the center of mass, and all of that's happening in my time interval. Well, I can also simplify acceleration of the center of mass even more, because we know that just the derivative of velocity over time is going to be equivalent then to my acceleration. So let's simplify it down once more. If I do that, I'm going to have my total mass times the derivative of my velocity of the center of mass, the velocity of the center of mass, over dt, and then again, all of that is in a time interval. So guys, all of that should be multiplied. Sorry about that. Let's go down here. So again, total mass times the derivative of velocity with respect to time, and again, all in a time interval. Well, if I simplify this down, that's going to leave me here, my dt's end up canceling out. And I know that mass, my total mass should remain constant, so let's pull that out of the integral. So I'm going to have my total mass, and then I'm ultimately integrating this velocity. So then that should simplify down into m times my change in velocities. So ultimately, we know that m times that change in velocity, and specifically here we're just talking about the change in the center of mass's velocity. We know that that's equal to momentum. So all we're doing is taking from our forces that are applied in a time interval and showing that ultimately we can derive that impulse should be equivalent then to mass times the change in velocity of that center of mass. And we've heard of this before. That's going to be our momentum, our impulse momentum theorem. So my momentum ultimately should also be equivalent to the impulse. And we saw that before. If we're just talking about single particles in a system, well, the same thing is going to happen when we're talking about center of mass. The total linear momentum of a system of particles should be conserved, and that's only happening if no net external force is acting on the system. Or another way to say that is if we have an isolated system. Because remember that an isolated system is just where we have a system where no external forces are acting on it. All of the forces are just internally acting. If we have a non-isolated system, that is where we're going to have external forces acting. So we may have air resistance, we may have friction, so we have some energy that may be crossing over the boundary from system to surrounding or from surrounding to system. So these hold true if we think about isolated systems where both my total momentum and then the velocity of center of mass can be constant in a time. So let's look at a conceptual example of dealing with for center of mass in terms of its motion. So let's say that we have a projectile that's fired into the air, and then this projectile just suddenly explodes. We have two different questions here. So the first question says, what can be said about the center of mass of the system made up of all the fragments after the explosion? So first of all, let's kind of assume that since it didn't bring up friction or they did bring up air resistance, that we're looking at just more of an isolated system here. So let's assume that we're going to not think about air resistance at all. If I disregard air resistance, then the only force that's really acting on the projectile is going to be gravitational force. If we go back and think about if the projectile doesn't explode, then it's going to continue to move along this parabolic path until ultimately it reaches some distance that in the diagram is just represented by r. Now, because the forces that cause this explosion for the projectile are internal, so there's nothing extra. There was no extra forces that were talked about in the first part where it says a projectile is fired into the air and suddenly explodes. There's no extra external forces that acted on that projectile to cause it to explode. That means that the explosion happened internally. So because the explosions happened internally, they don't affect the motion of the center of mass for the fragments. So after the explosion, the center of mass of the fragments are going to follow the same parabolic path that the projectile would have followed if no explosion occurred at all. If there was a net force, though, if there was a net force that was acting on this projectile that caused it to explode, then it would no longer be an isolated system, and we can't say then that it would follow that parabolic path. But because these things happened internally, we know that the center of mass is an isolated system. The center of mass is going to continue, for each of those fragments, will continue to move and follow that same parabolic path. Okay, so the next question says, if the projectile did not explode, it would land at a distance r from its launch point. So it would land right here. Let's suppose that the projectile explodes and it splits into two pieces of equal mass. One piece is going to land at a distance 2r to the right of the launch point. Where will the other piece land? Okay, so let's say that we are right here, and we know that this projectile is going to break apart into two small pieces. And those pieces are going to have equal mass. It says one piece will land 2r to the right of the launch point. Well, here's my launch point, and here's r, so then I need to go over another r here. I'm kind of limited by my screen here, guys, sorry. So I'm going 2 of these lengths, and that's where one of those pieces is going to land. So then I want to know where is the other piece going to land. Well, if we didn't have, let's say that we didn't have this explosion, we know that ultimately our projectile would just land right here at R. Now, one of those pieces now instead, now I do have the explosion, one of the pieces lands at 2R all the way over here. Well, this is an isolated system again. We already talked about that for the first part. And if it's an isolated system, I know that momentum must be conserved. So if they're equal masses and one of the velocity vectors will be moving this way, and I'm going a distance r away from right here if we're looking at this, because I know that ultimately if the projectile were intact, it would land here r. But now we're saying, let's just suppose that one of those pieces is going to move to r. Then that an extra distance here of r, if I'm thinking about this, is just my point. Well, if this is going to move a distance r, then that means that this mass is also going to have to move a distance r. But it's just going to be moving in the opposite direction for the conservation of momentum, so that way I can have my momentum be conserved. So if one of the pieces is moving to 2r, then the other piece must land here at my launching point. And it does that because I would have to have that momentum be conserved. Let's also look at more of a mathematical problem. Let's say that a rocket is fired vertically upward at the instant it reaches an altitude of 1,000 meters and a speed of initially 300 meters per second. It explodes into 3 fragments that have equal mass. One fragment moves upward with a speed of 450 meters per second, and the second fragment has a speed of 240 meters per second, and it's going to move to the east right after the explosion. What is the velocity of the third fragment immediately after the explosion? So I'm going to open a new page up so we can work on this together. Okay, so first of all, we know that we can assume that for the explosion, it probably happened in a very short time interval. We can, during the explosion, because the internal force of the explosion is what we would call the impulsive force, and that force would be much greater than the gravitational force or any air resistance. We can neglect those forces. So because the force must be internal, I can think about this as being an isolated system. So if I'm thinking about that in terms of momentum, then that should tell me that my change in momentum should ultimately be conserved, should be 0. Or I could say the initial momentum should equal then the final momentum. And let me draw my vector arrows above those. So ultimately I know that this rocket is moving as one piece initially. So I'm going to say that it's going to have a total mass then of, we'll just say capital M, because we don't have mass. They didn't give us that in this problem. And it has some initial velocity. So this is the total rocket. And that equals, it says that all of the fragments have the same mass. So then that means that each of the mass would just be, each of those fragments would have a third of the mass. So let's say that for the first fragment, we'll say it's a third of that total mass times the velocity of that first fragment, plus for the second fragment, again, it's a third of that mass times the velocity then of that particular fragment. And the same thing for the third fragment, it's a third of the mass times the velocity then of that particular fragment. Okay, well, let's simplify this out because ultimately we don't have mass, so we need to try to simplify this equation so that way we can get rid of mass because we don't have it, so let's just try to get rid of it. Again, here's the system initially. The rocket has a total mass moving with some initial velocity. Let's take out our third mass here, so then I would just have the velocity of the first fragment plus the velocity of the second fragment plus the velocity of the third fragment. So then if I divide both sides by 1/3 m, then that should leave me with 3 times the initial velocity equals the velocity of the first fragment, that should be a 1, sorry guys, plus the velocity of the second fragment plus the velocity of the third fragment. Okay, well we know some things. We're trying to find ultimately this, trying to find the velocity here of that third fragment. Now, these are in different directions because initially it says that my rocket is moving upward, and it was initially upward at 300 meters. So VI is equal to, 300 meters per second. So VI is equal to 300 meters per second, but that's in an upward vertical direction, so I need to designate that. So let's say that this is now 300 J roof meters per second. So let's plug that in here, 3 times 300 J, and that's in meters per second. And that's going to equal the velocity of the first fragment, which they also gave us, and that one said that the fragment was moving upward. So V1 is also moving upward, and it had a speed of 450, so we'll say that's also J roof. So that would equal 450 J roof meters per second. Now the second fragment, though, it's moving eastward, so that fragment is moving eastward with 240 meters per second, so then that means I'm going to designate that with I roof. And then we're trying to find the velocity then of this last fragment. So if I simplify this down, I'd have 900 J roof on the left side of the equation equals 450 J plus 240 I. So then if I subtract the 450 J from the right side, I'm going to end up with 450 J roof. I want to subtract the 240 just to get V3 by itself, so minus 240 I roof. All of that then is going to equal my velocity of that third fragment. But we always wanted an XY notation, so technically it should be negative 240 I roof plus 450 J roof. And then let's denote that's meters per second for the both of them. And that's going to be what my velocity of that third fragment will be. So most often when we're talking about our motion of particles, we usually think of these systems of particles as being non-deformable systems. But what happens if we have a deformable system? So, for example, let's say that you're on a skateboard and you push off of a wall, and then when you're pushing off of that wall, then ultimately you're setting yourself in motion that's going to be moving away from the wall. Technically, your body has deformed during this motion, and ultimately our arms were more loose and kind of bent as we're moving towards the wall, but then when you're pushing off of the wall, your arms had to completely straighten out and exert some force on the wall to push back off of the wall. So usually we find that with deformable systems, we cannot use the work kinetic energy theorem because typically what will happen is the work that's our work technically ends up being zero, because technically the object that either we're pushing off of, so let's say the wall, the force from the wall on our hands, if we're pushing off while we're on our skateboard, doesn't move through a displacement. So since the force from the wall moves through no displacement, because we know that work is equal to force times displacement, technically the work there would be zero. But we know that we have a change in kinetic energy because ultimately I had a resultant kinetic energy from pushing off of the wall. I know that my speed is going to change as I'm moving away from the wall, so I know my delta K changed. So unfortunately for deformable systems here, for work equals our change in kinetic energy, it's just not going to hold true. Instead, we can think about the energy of the system in terms of the sum of all the energy transfers. So we're going to think about this equation here, and that's just saying that you already know that our K are, this should be, sorry guys, a delta K, our change in kinetic and our change in potential. Our change in kinetic energy is just going to be related to increased speed of the system. So I was going pretty slowly on the skateboard as I moved up towards the wall, but then I pushed off of the wall, and now I'm going to have a change in kinetic energy because I'm going to have a much faster speed as I'm moving away from the wall. I also have a change in potential energy because I know that I have stored energy from food that I've eaten in my body, and I'm going to have to exert some of that. So I'm going to have some change in potential energy as well, because I have to have some muscle exertion as well, because that's necessary to push off the wall. I could also apply change in momentum, and I know that my change in momentum is just equal also to impulse, so I could think about the mass times our velocity, which would just be my momentum, is equivalent to the force that's being, the external forces that are being applied in a time interval. So I could still apply something for deformable systems. One big thing I want you to know is that we will not be able to use the work kinetic energy theorem. So the last section in Chapter 9 is just about rocket propulsion. It's not a very long section, so we should kind of get through this pretty quickly. If we think about a rocket, then we know that a rocket is going to have the mass of the rocket, plus then we also think about the mass of the fuel that's ultimately going to be ejected from the rocket as it's propelled. So when we think about the initial momentum of the rocket, then we think about the combined mass. So we have this capital M here, which is representing the mass of the rocket, then plus the change in mass here, and that's just going to represent the mass of the fuel, because the amount of fuel in the rocket's constantly changing because I'm ejecting that fuel out of the rocket. So its initial momentum is going to be the sum of the masses, so my mass of the rocket plus the mass of the fuel, and then times some initial velocity here. Now, we know that as time moves on, the rocket's mass is going to be reduced, because ultimately I'm going to lose all this fuel here, what we just have symbolized as delta M. All of that's going to be ejected. But as I'm losing this fuel, ultimately we know that as a rocket moves in free space, what will happen is that its linear momentum is going to change because some of this mass is being ejected. Because the gases are given a momentum when they're ejected out, we know that the rocket is going to receive a momentum in the opposite direction. So the fuel that's leaving this way has a certain momentum, but now that's giving the rocket even more momentum than going in the opposite direction. So because we're losing the mass here, we're gaining some extra change in velocity for just the rocket itself. So we have a basic equation for rocket propulsion, and that's just simply the final velocity minus the initial velocity is equal to V sub E is just representing the velocity of the escape gases. So that would be all of that exiting fuel that's coming out. And that escape velocity of those gases is going to be multiplied by the natural log of... There should be a divided sign there, guys, sorry. So the natural log of m sub I over m sub f. Well, m sub I is just representing the initial mass of the rocket plus the fuel. So that would be the mass of the rocket plus any of that fuel initially that the rocket had. The final mass then for the rocket is going to be the mass of the rocket. Then if we've got rid of all of the fuel then that we wanted to for those that we'll have at our escape gases, that it would just be the mass of the rocket, but we'll probably have a little bit of residual have a little bit of residual fuel as well, so I'll make that one just like a little bit smaller. So just whatever fuel is just left over then would be the mass for the final mass of the rocket. If we think about in terms of our velocity of the escape gases, so it says that the increase in rocket speed should be proportional to the speed of the escape gases. So this should make sense that if I have a large speed for the escape gases, ultimately I know that momentum has to be conserved. If the escape gases are moving out quickly in one direction, the rocket is going to be moving with a similar speed then in the opposite direction for our momentum to be conserved here. So our escape gases should have a fairly large speed. And the increase in rocket speed is also proportional to the natural log then of my masses, so the initial mass over then the final mass. And ultimately, we want this ratio to be as high as possible, which means that the mass of the rocket should be as small as possible, but it should try to carry as much fuel as possible. So finally, we have thrust in terms of rocket propulsion, and thrust on a rocket is simply the force that's exerted on the rocket by the ejected exhaust gases. We can measure thrust if we take the mass, so we have m dv over dt, or that could just equal then my velocity of the escape gases, and then that ultimately by dm over dt. So the thrust increases as the exhaust speed increases. So as I have more of exhaust speed, this will also increase, thus being the directly proportional. We could also call the rate of the change in mass, so that would be my dm over dt. The rate of change of mass, we call this the burn rate. And the thrust will also increase as the rate of change of mass, so this dm over dt, as that also increases. Okay, so the last problem, or the last slide on this is an example using some of the rocket propulsion formulas. So I would like you to try these for me and bring them to class, and we'll work on these, or we'll look at them and go over them together at the beginning of class tomorrow. Actually, the beginning of class tomorrow, you'll have a small formula quiz. I will add to Quizlet the few formulas that we did for this particular video on Quizlet tonight, and show this to me after we get done with our formula quiz. I'll also post some practice questions for your test on Thursday. I'll post some more information about that on your blog tonight as well. I hope you guys had a great day. I will hopefully see you tomorrow. Bye.